Today's lecture, I'm going to be talking about the design, fabrication, and construction of flow bridge. The format of the presentation will include going through the design processes, the challenges, fabricating the bridge, and constructing it, including modifications that took place for the design. The modifications would be going back and forth in between the design because there's a design for trial erection at the long masting site, and then that was followed by the taking it to a shed in Melton Mulberry for modification works before I went to the library where we stand still. So the presentation will go through all of that. The flow bridge is an innovative modular concept footbridge was developed by Network Rail, and the initial purpose of it was to find a low-cost, effective solution for closing unsafe footpath level crossing. So to give a synopsis, it took us 11 months from developing the concept to fabricating it on the test site. And that was also, the design was done during COVID as well. And it was first open to the public during Rail Live in 2021. The design takes a different approach to modular by looking at various concepts and adaptability that could incorporate a steered version, a lift version, and a ramp version. But for the purpose of this presentation, we'll stick with the prototype, which is the S-shaped version of the flow bridge. Right from the start, the site selected for the footbridge was a non-station environment, which had a dangerous footpath that had been temporarily closed. So we wanted to use this as a test site to demonstrate what this can do. The objective we had was to develop a low-cost weight-light footbridge that was resilient, more durable, very easy to maintain, and easy to construct. We also wanted it to be an enabler to enable us achieve Network Rail net zero targets, which is to have costs reduced by 30%, carbon to be reduced by 50%, and the concept will be developed from inception to entering service within a year. So as a result, some of the criteria for the design meant we had to limit the maximum weight of any modular unit to 2.5 tons to allow RRVs to install it over the railway. And finally, we wanted it to be something that looked good, so that would be accepted in local communities and by the planning authorities. The main challenge we had was right at the start of the project, COVID struck. So there's no way of meeting each other physically. So we had to find new ways of working together. Another challenge we had was with FRP design, there was no structural design code for FRP design. We had guidance documents, and at the time of the design, the main guidance document was the series C779, and we had Eurocomp and other design codes. So what we had to do is look at those with the existing guidance we got for steelwork design and Network Rail standards and other guidance document to try and figure out how we can get this design done. There was lack of manufacturer's data, EPD data, and so it posed a lot of challenges. And we also wanted this footbridge to be a game changer to showcase what's done in composite. Rather than copying traditional steel design, we wanted to utilize the material for what it is, which is a material that has a high strength to weight ratio. So we thought the design ethos should follow that. So we had no dedicated team in place. So what we did was we had to build the team through together. But the other challenge we had was securing funding. So we managed to get funding from the R&D Research and Development Fund, which enabled us to do the design. To do that, we wanted to innovate right from the start and do something different. And lessons learned from past projects showed that 60 to 80% of project costs occur during construction. And a lot of time, the project cost exceeded the target cost, reducing stakeholders' confidence in our ability to develop projects on time and within budget. So one of the things we did is Network Rail took on the design and construction lead by taking these risks. And then by having the research and development funding, that simplified procurement a lot, which meant it allowed us to find the relevant small to medium-sized UK enterprises with the skills that we needed. So we from the start, we had Network Welder in the middle, and then we had Nice Architects, who is a renowned architectural firm. So we engaged them to help us with the architectural aspects. And then we got Sui Generis that do design baffle tanks and boats. So we got them on board to help us with the fabrication of the superstructure deck. And then we got Jacobs, well-known engineering firm, and they got a lot of expertise in FRP. So we got them to be the category 3 checkers. G-Railing provided the glazing system that we had for the design. KS Composite, they actually make Formula One cars, but their knowledge in composite meant engaging them would be really useful. So they were involved in fabricating the spine, the pier legs, and the carbon Kevlar hinges. Structural Soil Solution, or JTC Consulting, were involved in the Rapid Root Foundation System. Again, another innovative solution system. Then we have Full Flow, which is a small to medium project management company that managed the whole risk for the whole entire project, tracked the risk, did the KPIs, and made sure we're on track. And we had Epsilon Optics that actually developed the fiber optic system for the structural health monitoring system, because it's a new design. We wanted to understand how it works and behaves so we can continue to improve on the lessons learned from the behavior. And then we had a Perry, maybe that we utilize the temporary prop for the design itself. In this design, we utilized different ways of working. We had a canvas board because it was during COVID. Most of the design was done across Teams. Meetings were done through Teams. We communicated with each other through Teams using whiteboards and having a chat. And then the way the design worked is the designer and the checkers worked in parallel. So whatever concept we had was discussed and agreed with the design checker. And then we did those design and it was passed straight away, rather than do the traditional approach where you do the entire design and it goes to the checker at the end. With this design, we're working in pass, so it meant we saved time. And we also adopted a culture where there was a no-blame culture. Everyone had a common vision to make sure we deliver the goals and everyone's valued. When we encountered a problem, we just came together and resolved it to solve a solution. So this slide shows the early concept that was developed. The diagram shows the evolution from the team on the concept that was developed by Knight Architects. So rather than having a normal rectangular plan footbridge, we looked at how we could improve on the visibility and the aesthetic as people and the user experience around the bridge. So Knight Architect came up with this format, which we looked at, and it had vertical legs with a cantilever spine. But there was a couple of challenges. The curve bit was not connected to the spine, so it was floating. And then so we looked at that initially and did some analysis and found out the deflections on that cantilever bit alone was about 72 mil, which meant the main span deflection would be even higher. So that's that challenge. And then there was also a risk of people climbing on the legs if we brought it too low down. So to resolve that, we then basically worked around that by coming with different structural form on that pair leg support to enable the bridge to be a bit more functional. So that slide shows the form we came up with. The solution was to have inclined pair legs in there, which had an arching effect, transmitting most of the loads in compression. We also had gussets there with stiffness. I'll talk about that in a later slide. To allow a smooth transition of the load and disperse any stress concentration between that pair leg and the spine. And we also looked, that same effect was reversed on the bottom stairs. And one of the advantages with this form of construction is normal footbridge of this size will have 6 footprints for the foundation. We minimized that by just having 4 footprints. So that was one saving. The second thing we looked at was the deck itself. We wanted the spine to be a temporary, to provide temporary support for the bridge as well as permanent support. So to minimize the amount of temporary works, we had a gravity clamp system for the deck where the deck would close and lock over the spine, and then the deck slab locks it in place, effectively making the structure composite. And I'll talk about that in the next slide. So this diagram that we're looking at there just illustrates how the bridge itself works. The philosophy. So we have the yellow bit being there, the spine itself with the deck over. We have a Kevlar hinge carbon Kevlar hinge that runs along that side there, which allows the deck to open and close. And I'll talk about that in a later slide. And then we've got everything in this unit was fabricated, so nothing was protruded. It was all made by specific design. And then the deck acts in tension, and then we then have the unit basically coming down, locked in position. With the FRP angles that in there, they attach to the side of the deck unit, and then the deck unit is bolted in position. The spine is designed to support the weight of the modules during construction and act compositely once everything's put in place. The modular spine basically is done in smaller pieces so they can be transported and assembled on site. Part of the design meant some of the connection had to be done in factory and some were done on site. So the image on the right there shows a factory bonded connection where we had an internal sleeve at this location there with knot plates and bolted connection adhesive. So it was designed to be adhesively bonded as well as bolted, and both the designs had to satisfy the design code. And then the rest of the elements where you're looking at for the site-based connections, we utilized bolts, but we had a debonding layer, so the adhesive in between that was like a gap filler to allow the loads to be transferred, but keep the unit kind of nice and tight together when bolted together. We utilized a 3D parametric model for the structure, and that was created by Knight Architects. So that created a virtual environment to enable us test any concept we had in the design and validate it. And because we're working remotely as well, it was a useful area to check to make sure that clashes or anything that could cause problems when we're on site were identified early. So for the temporary props which we look at, they were tested and designed within this environment and then applied on site, and that worked well. A lot of the fabrication drawings and design drawings were then produced from this model because they had every single element, and that just made things seamless in terms of utilizing the detail and then detailing it. For the spine legs and the pier legs, we produced some of the drawings and some were produced by KS Composite. The philosophy of this design, when we looked at it, was to enable the spine to act as a temporary structure to facilitate the construction works, and then in a permanent condition, work compositely together with the spine afterwards. The spine also enables us to correctly align the bridge in position as you go along, and it enabled the bridge to be stable at all stages of construction, meaning if we decide we're running out of possession, we can secure the site and leave it over the railway and it'll be safe. And that was a big game changer because a lot of the issues we normally have is disruption to the services. So we wanted to minimize that. For the design itself, because it was a new material, we had to limit the strain of the material to 1%. And because the material was not validated by testing, but we're using manufacturer's literature, we had to use higher material partial factors of safety as per the requirement of CA guide. And the hope at the time of design was by carrying out testing afterwards, when we do the second version of the bridge or a standard version, which is currently being done now, we can then reduce these factors of safety to make it even more efficient. For the bridge design itself, when the units come in, we took into account the safety of the workers. So we had the unit installing with the side parapet and edge protection. And we also had brace points for people working in it, so they could basically click on the harnesses at those locations while they're walking in there safely. And for fire classification, the site chosen for this bridge was a non-station environment. So we looked to achieve a classification of class CS3DO for a non-station environment to BS 13501. So other design considerations we looked at when we're designing the bridge was to ensure that we wanted to ensure that during the temporary condition in the factory, lifting conditions, storage in the cradles were already being sorted out. We also wanted to make sure that when they're lifting the bridge during construction, that and the stage construction by RRV, we had to look at that temporary condition and also maintain stability of the bridge to when it's put in over the spine, and also for the permanent condition when it's acting compositely with the design loads. Then on top of that, we also wanted to ensure that when the bridge is inspected in the future and maintained, if certain aspects of the deck elements want to be removed, we wanted to make sure that they can be removed safely without compromising the safety of the bridge itself. So just going into composite itself, one thing to clarify is this is not like steel or concrete. So every single material on that bridge had to be designed. The way the composite works is you have a fiber and then you have a resin, and then you combine the two together, and that basically gives you a composite. And depending on the plies you have for that composite stack, you can lay the stack in different on top of each other with different angles, different orientation of the fibers, and depending on how you do that, it gives you mechanical properties. So the fibers provide most of the strength. The resin or binder allows for load transfer to the fibers, and depending on its properties, it can provide environmental properties such as temperature resistant, chemical resistant, and so on, and sometimes fire resistant depending on what you put on it. The advantage of this material is got a very high strength to weight ratio, so we wanted to capitalize on the material properties for the design. If you just use the laminate on its own as a monolithic laminate, it's strong, but to gain more efficiencies and reduce costs, what we do is we have a sandwich approach where you have different skeins of composite with a sandwich core in the middle, which is very lightweight, and that enables you to have thicker sections, which give you better engineering properties, but at a fraction of not making it too expensive. So for the design itself, we utilize biaxial laminates. So the laminates could be at plus or minus 45 degrees, as shown there, or it could be plus or minus, it could be 0 degrees and 90 degrees. And we also utilize quadraxial laminates, which is 0 degrees, plus or minus 45, and so on. For the flow bridge itself, just to put things in the concept, for the spine design, we actually had 16 different types of laminate. Some of these laminates had foam cores in it, some didn't. And for the deck itself, we had 15 different laminates. This diagram just shows an example of typical laminates that we utilize for the bridge design itself and the thicknesses. And one of the things we did was, with where the deck was being made, we had a layer of where the gel coat on the outside, and that gel coat is what actually provides the waterproofing to the laminate, and it protects against breakdown of the fibers, UV degradation, and it can also incorporate the color of the structure that you want. And then followed by that, we had layers of chopped strand mat, which allows a smooth surface for the gel coat to bond to. Then you have your fibers themselves. So you can see the gel coat there, chopped strand mat, and then you got your main structural fibers coming in there with the core in the middle, and the same happens the other way. So for this approach, we had a balanced laminate where we had equal laminates on each side, and then in some areas we didn't have that. For the spine gusset pair legs, they were made with biaxial glass, and the orientation of the fibers were designed depending on where it's required. So for the heel, for example, we had carbon Kevlar at 0, 90, plus or minus 45, depending on where it's needed. All the joints where we had bolted connection had no core in there because we wanted it to be solid, and we didn't want to have issues with stuff cracking along those locations. From the analysis point of view, we utilize Lucer software for the main structural analysis, and we utilize robot software, which I'll talk about later again. The glazing self-weight, what we was added onto the model by putting the self-weight onto dummy members which were beams on the top of the parapet itself along that length, and the associated vertical, horizontal loads and moments to go with those were then applied on those elements. We use shell elements for the deck itself, for the global model, and then we use beam elements for the spine and the pier legs and support. We then created a separate FA model for the pier heel at that location, which is there, and the stair heel there, because we wanted to understand the effects of them locally. So we then utilized the boundary conditions that we had from these, calibrated it, and then analyzed these separately so that they could be designed and checked. We did hand calculations to validate what we've done to make sure everything's fine, and the analysis included static, dynamic, nonlinear analysis to check for buckling, the construction sequence, and other analysis as well. The pier heel, just going to expand a bit on that, we initially wanted to have steel plates with steel stiffeners on it, with steel tube at the bottom there, and then wrap it around with some form of foam, and then maybe glass fibers and exterior protection. That was the initial design philosophy that we looked at. But when we analyzed that, we soon found out that the stresses were exceeding the stress for the plates, the steel plates that we had there. So we did an independent check from robots using Lusas, and we had the same result as well. And then we checked that with the checkers with Jacobs, and they confirmed the same thing as well. So this is where working with KS came really handy. So the innovation paid off because we worked then with KS Composite to develop the pier heel stool there. So we came up with that concept there, and then that was then cleaned off and then by a nice architect. And then we looked at the practicality and how we can put this together with KS Composite. And there are a lot of solutions that were developed. There's some of the solutions, something we never come across. So on the bottom bit there, the solution was to have the top bit there, this bit with a foam core interior CNC to get that shape. And then you can drip the carbon over it and the Kevlar. And then the green bit there is a steel insert that was machined with a threaded piece in there, and everything will be molded and wrapped around that. So on that base plate there, that was steel, we had an inner array, circular array of bolts, which allow you to fix the top bit to that, and the outer row array of bolts basically allow you to secure it to the foundation. And the same concept was developed on the stair heel as well. And on the left side there, you can see the actual bits being done. One thing we did when we did the analysis was we had very high stress concentration due to this sharp corner there, and we couldn't get that to work. So the solution was to shave that off, do the analysis, and that worked. And then we added this as a cosmetic piece, which you can see on the slide on this picture on the side there. Dynamics was a really important thing for the design because of its lightweight and everything. Dynamics, one of the critical load cases. So we wanted to make sure that the vertical frequencies exceed 5 hertz and the lateral frequency exceed that. So when we did the analysis, we checked all the different modes, and these were the ones that were propping up. So we found that mode 1 was critical because it was a vertical frequency that was less than 5 hertz. And to enable us to understand that, we had to look at the modal displacements as well. So we then plotted that for all the modes and had a look at that. And then you can see on the mode 4 that you get in both vertical and lateral and vertical there. Well, so we had to check the acceleration limits for the comfort criteria for this in accordance with the code. So we did those checks, and then we found out it was okay for the bridge class A in dynamics. This is just some videos just to show what was picked up from the dynamic analysis and how the bridge behaved. And that's just to show on plan. So for us to do that, we had to have an overall view of all these bits, put it together to see how the bridge behaves. Another area of the bridge design was the wind loading and aerodynamic. Because of the complex shape of the bridge, it's really difficult to actually understand how you're going to apply the wind loads on the bridge. And so we wanted to minimize the amount of load cases we had for wind and aerodynamic load. So we then put a 3D model of the bridge within robot software, which has got a wind tunnel simulation module in there. And we carried out the analysis on that. And this is just some shots to show the critical areas identified. And that helps us minimize the load cases we needed for the analysis, because we can then apply those loads directly in our load combinations to simplify things. In the design stage, we will look at the initial design. We wanted our foundations to be on a fixed hill, but when we looked at that, the moment meant you needed a much larger cruciform base. So we will require 2.5 meter cruciforms, which were enriching the footprint of the railway. And part of our design was to minimize that impact. So we had to look at ways of reducing that. So we carried out sensitivity analysis on the fixicity of the foundation, as well as the lateral spring stiffness, based on the stiffness of the pile group that we had with the pile designers to determine what was the most efficient way of reducing that. And we found out by having a pin support, we can reduce it from 2.5 to 1.5, which seemed reasonable. And we achieved the pin effect by putting a C40 grade neoprene under the base plate of the foundation, which sits around that location there, and then bolt it onto that. And the deflection of that, which is similar to how elastomeric bearing works, enable us to get the right rotation for the design, and we were okay with that. This just shows the idealized construction sequence we had when we did the design. So we had maybe props in there. Just note the size of the maybe prop. They posed a lot of challenges for us when we were constructing it because of the bulky nature. It was difficult maneuvering that V-leg over that, and we had 2 locations for it to rest on. And that prop actually helps us align the position of the bridge as well. So if you get it wrong, you wouldn't get both sides aligned. We had to utilize a balanced construction method to minimize the deflections. So if you do one ramp on the left side, you're going to do the other on the right side, and then the deflections cancelled out. Now we're into fabrication. On the top left is a CAD model of the mold for the one of the deck units, and the middle is seeing the actual mold of a curved deck being produced. One thing to notice, this is a temporary mold, so it's like designed for one use because it's made of timber and plywood. So it's the cost between that and it's slightly expensive to get a more expensive mold that lasts longer. A more expensive mold will allow you to make 10 to 15 pours of that mold before you need to repair it. Whereas this one mold and it's gone, one pour and it's gone, because it causes the moisture and everything else. When you put the laminate in, it causes the timber to expand, and then you can't use it again. On the top right corner there, which is what you're seeing there, you basically seeing the first layer of gel coat being applied, and on the bottom left, you've got 2 layers of gel coat being applied, each approximately 0.6 mil thick. And then on that slide there's a bonding paste being applied, ready to receive the foam core on the side of that deck unit. On this bit there, you can see the ribs, the carbon fiber ribs there. They're solid, they've got no core in it, and a bonding paste will be applied to the side and the corners using a special spatula to enable it go around the bend. Otherwise, you get cracks forming. So you get a nice smooth bit. And once the bonding paste is done, the laminate laps will be then put in, which you see on the following slide. On this image there, you can see the unit being released off the mold, and just lifted initially just to test the lifting straps in as it's been done. And on the image on the left there, you see a ramp module with the gel coat being applied on it. And on the right side here is a mold for the side fascia panel, as well as the supporting bit for the step unit for the ramp. As mentioned before, in here you can see the carbon Kevlar unit hinge being applied. So it's added in afterwards. And as I mentioned before, you can see the additional laminate layer there that's added either side of that, of course, there to bond that securely to the deck unit. And where you got these holes, the special lifting eye locations for lifting the bridge. So we've got additional laminates there that's been put in there to secure it as well. And I'll show that on the next slide. On this slide, the elements there, but you can see the edges being rough, so they need to be trimmed off and grounded, and then it'll be ready to go on site. In here, you can see the support bracket for the decks made from GRP. Again, these are not pulled through the section. These are made from quadraxial glass fiber. So it's been specifically designed for the loads that we've got. So they've been bolted on either side of the ribs ready to receive the deck, and the bolt on the top of the deck to receive the deck slab that's coming in. And this image is just showing the interface where this mold is being released. So just to show the finishes, and that is the nib that locks into the spine when everything's in position. So in here, we've seen this is a typical mold for the deck slab. We had two types, an 800 mil wide one and a 1600 wide one. This is a 1600 one. And on the right image that you see there, it's just been released from that mold. So you can see the plugs in there. These plugs have recessed areas that allow the bolts to go through. And this has got a sandwich core, or where you got the connections and everything. It's a solid core. It's got no foam in it. That's just showing you the deck slab units being put in position with the holes in place. One of the lessons learned in the factory was when this was done in the factory, it was done on a flat surface. So there's no deflection, but when you go on site and it's on the spine, you're going to get deflection. So to allow for that, we had a slotted hole put in that position there. But once that was done on site, that hole was then filled with liquid metal filler or liquid putty to seal all that holes to make sure that nothing, you got the right edge distance and bearing for those bolts at those locations. On the left, there's a stair mold, and the right showing a stair module being released from that mold. And that's just a curved unit on the factory on the left being put together and tested. So we had bolted connection between each module along the interfaces of the ribs for continuity. And on the right side is just showing the module being moved around with a lifting point. We provided additional holes in some of the units. That's areas for where people walking on the bridge can click on their harness and support themselves there. So when they're walking towards the edge, they're protected against falls. Next slide showed in the factory, we had a ramp unit put together, and then the stair modules and side fascia panel were tested in the factory to make sure everything fits perfectly before, with the holes being drilled before it was taken on site. And on the right is showing the stair heel being put in position, basically, and locked in position before other bits of work are put into enhancing it. This bit is looking at the fabrication of the pier heel. So on the image on the left, we utilize carbon fiber and Kevlar in between for constructing this hinge. We had a CNC foam that was CNC'd for the shape, and we utilize a pre-preg laminate. So pre-preg carbon and Kevlar were laid over each one of these, and then after that, put in the vacuum bag to remove the air bubbles and get them to stick together. And once that's done, they were then transferred to a high temperature chamber and cured. And in that temperature, the temperature is raised to 130 degrees. Once the tooling hit that temperature, they were cured for up to 3 hours then, and then it was taken off that unit. So the image on the left showing the draping of a carbon along that pier here, and the right showed a cured unit that's come out of the mold ready for the works. On the left is a typical fabricated spine. So you can see it's got glass fiber interior, and we utilize flax fiber for the exterior. Flax wanted to provide a level of aesthetics on the bridge as well as protecting that. And then you can see the gussets there and on the curved spine and the top bit of the curved spine. So they're waiting to go to the next stage where they're going to be bonded and bolted together, and then that will form part of the curved unit for the deck. On this slide, you're seeing the rapid wood steel cruciform being fabricated. So you can see this is missing the top plate. So in here, you got the finished unit there with the pipe crosshead. Obviously, this is not the one we use for withstands to bore. It's just to give an illustration of what they look like. And in here is basically the trial installation of the bridge itself in long masting. So after 9-10 months, on the 11th month, from the concept developed to fabrication and check-in, we had this built on that site. So this was done during COVID. So on that image, we put in the curved spining. So the legs, the heel, the base plate, as well as those bits were assembled on site and then lifted up by an RRV and dropped in position. And then you can see they may be prop there, so it's quite bulky. So it's quite a challenge putting that around that. So that meant we had to. It was one of the to-do list. Tick it, see what we can do to make that better next time round, and that shows everything being put together, and then the deck units being installed, and the units were installed without the glazing at this stage, and then the glazing done afterwards. So that it took us 3 weeks in total for constructing the whole bridge. And the sites. This site was a test site. It wasn't a live railway site, where it enabled us to simulate what it would be like building the bridge on a live railway site. And then we had 2 to 3 days delay of weather, which prevented works being done. But even with that, it was really good. And when the bridge was constructed, before the deck was put in, all the structural health monitoring was installed, calibrated, and tested. This just shows Longmaston test site with the units being installed and testing the glazing on. One thing to note is we had very cheap saddles supporting the bridge, and we had them done like 2 or 3 discrete saddles made of OSB board, so they were cheap. Now, the disadvantage with this is when the ground is uneven, you can see in that image there, it's causing the carbon Kevlar to twist, and in some cases, it started causing them to delaminate off what we had. So that caused us to review the design ethos that we had before and make sure we can correct those before we come back to site. This is the finished product. As you can see, the deck was done by a different manufacturer, spine different manufacturer. We never met, but because we did it in the 3D virtual environment using the drawings, the beam drawing, everything fit perfectly when we got on site. We then dismantled the structure from Longmaston, and then we took it to a shed in Melton Mulberry, where we installed the bridge to carry on modification works and improve what we did. One of the first things you can notice is we've changed the prop. So we have a much smaller prop system there, and which a peri prop system, a triangular base system. And then at the top, we designed a carbon Kevlar and glass fiber saddle. That saddle follows the contour of the spine with steel base plates there following the alignment, tapered plates following the alignment on each side. That enabled us to basically, once that was set, we could get the spine orientation right. And then because the level in which stands to now, it's actually the track levels are 1.5 meters higher than the level of this foundation. So to accommodate that, we had to design stools for the bridge itself. The stools for the support in the bridge had to be designed such that the deflection at the level of the base plate will be no more than 2 millimeters. Otherwise, we'll start having, and it will affect the entire design that we've done. And we didn't want to do that. So we then had to look at that to see what we can do. We then installed the units in here with the glazing on each module, leaving the end modules out, because to save time on constructing, we wanted to see how that was possible. The lifting points were designed to take the entire load anyway, so that helped us. So we're able to rehearse and practice how the bridge was put together within the shed before we got ready to go to with standstill. In there, you can see the units being loaded into the back of a truck. Now you can see specially designed saddles there, all designed to work together as one. So it's a lessons learned to make sure that the unit is intact. We also had temporary bracing at the end of the units to secure them in place. And then we had additional bracings within the unit itself, which I'll talk to later on. The end units were removed to prevent damage during transportation. And when we're lifting it, we didn't want it to clash with the other units, so we removed them, and these were done on site. So we will actually minimize the amount of construction work that was to be done on site. But now on site, while that was going on, the site work started with rapid route, where we had the piles driven through, and then that's the cruciform head being dropped in, lowered, and bolted in. The vertical adjustment for the levels is accommodated by these bolts there, so you can lift the cruciform up and down. But then for the lateral adjustment for setting out, we accommodated that within the pier stools, and I'll talk about that when I go through the next couple of slides. The advantage with this is it can be driven by a 20 to 30 kilogram self-powered driving hammer, and it drives these tubes down to depths of approximately 1.8 to 2 meters below ground. It's got very little impact on the railway itself, so the whole works was carried out while the trains were traveling. So you can see the site there with trains going through, with the 4 cruciforms being completed, 1, 2, 3, 4, and you got the site there. And then that allowed us then for the construction works to start. In here, we got the stool that was designed. As I mentioned before, to minimize the deflection, what we had to do was put a circular hollow section tube. Then we had a universal UC column welded on the bottom and the inside, and that was infilled with resin to enable us minimize that deflection. Otherwise, we wouldn't have got that for that height. And then we then had a dense foam core to create these shapes, which had pockets in there to allow us to put the bolts. On the bottom, we had a bottom plate, and that had slotted holes, so it allowed us to move the bridge transversely that way for setting out to get the position of the bridge right. And then on the top adjuster plate, you got the movement, which is there. It's the opposite direction into the page to allow for the other side of the transverse movement. And what we did with that design was the neoprene here was there, and then the pier here base plate was bolted onto that, and then with the packing plate, and that was all lifted in place and dropped in there. And once it was in position, bolts were then put through to hold us in place, lock it in place, and then it was then bolted and secured through this bit that we provided there. The same analogy applies for the stair here, but it was because it was a rectangular arrangement, it was stiff enough, so we didn't need anything inside. We just had to infill it with resin to get the mass that we wanted to work, and the design follows the same principle. So now, when we stand still, after that was done, we had a couple of possessions. So the temporary prop was then installed because the foundations were installed for those alongside the cruciform foundation. So on the first possession that we had, we installed the props, and then the spines were lifted, the curved bit were lifted in position and dropped in position on either side by two separate teams. And then once that was done, we then install the ram spine and then the middle spine last. As mentioned before, you can clearly see the level of hair that's lower and the track level will be much higher in there. So the temporary spine prop and the spine were installed just over one night. In this slide, I just wanted to go through the temporary works on the bridge itself that happened. So at the end bit there, you got end brakes, which you can see in there. They're there to secure the units during transportation and storage on site, and they were removed before we lift the unit. We had steel mechanical hinges there. There's one there and one there. So on the plan, it's one there, one there. Two per location. They're designed to stop the carbon Kevlar hinges from twisting in case they're stored on uneven ground, so we wouldn't have the same issues we had with the long masting install. And then we had these little bits there. They're like cleats, steel cleats, which were bolted onto the side. So you go 1, 2, 3, 4. And then we had these shackles on either side with a chain and a ratchet strap in the middle. And the ratchet basically works by closing and opening. It allows the deck to open and close, and then giving us proper control of how we open the deck when it goes over the spine. So before lifting, the deck was open on the lift up a little bit and opened, and then it was lifting position. And once it's over the spine, the ratchet was closed, and then it clamped over the spine. And then once that was done, end bracing was put in at the edge for edge protection, and then the shear logs and other things were installed and necessary bracings installed. So that just shows you how the deck opens and closes. So it was limited by 6.7 degrees. On the mechanical hinge, it had limitations on it, so it only allowed you to open it up to that amount of rotation. Any more than that, there's a locking mechanism that stops it from going in there. And the lifting areas that were strengthened with additional laminate, so you can see a laminate on either side lapped across there to reinforce that area. On this slide, you can see the deck units being dropped in over the spine, locked in position there. Once it's locked in position, the other side's done, so you can see on the opposite picture. And then we had two teams working in sync, following the construction sequence, and the next first curved unit was dropped in. At the interface of that curved unit with the ramp unit, the end rib has got holes alongside the ribs there. We had bolted connection connecting those two together, so that provides a longitudinal connectivity. and then the shear lugs were then installed on the inside of the unit to secure it, and any permanent bracing was then put in within the deck unit to secure them at the right locations. And at this location there, you can see the units being installed, and you can see the end brace there, which is providing the edge protection. You can see a bit of harness, a rope there, which the people working attach themselves to, secured on the deck. And yeah, and that shows the whole unit being done. We would have finished it in the second possession, but what happened was gypsies actually stole all our bolts for connecting that third unit in place. So when we went to look for it, we couldn't find any of it because they'd been stolen on site. So I think someone left them outside. So we had to postpone it and come back for the third possession to put that in. After that, the rest of the glazing units were put in between these units with cherry picker, and then you can see it all being finished there with the site being handed over. And then before handing over the site, the deck slabs were then put in with the side fascia from the center of the deck, walking outwards. And then this bit hasn't got the step unit installed yet, but we had anti-slip surfacing in there to help people walk through the deck and prevent trips and falls. And then that's the completed structure overlooking the pond. We had flex MSC reinforced earth wall there because the level here was a bit higher. So we had to accommodate that with that bit there, accommodating it down as part of the design. And then that's the bridge open to the public, in which standstill, and it was well received. So just as a quick summary, it took us 11 months to develop the concept, from concept to fabrication and design during COVID. The actual bridge itself weighed 25 tons, of which 5 tons the glazing. It's designed to utilize glass panels, or we can use composite or other panels, infill panels. Normal steel structures weigh around 35 to 40 tons, so that was quite good. The cost itself is 30% lower than a typical steel footbridge. The modular components meant we had a quicker build in the components. In the trial install, we had 2 to 3 weeks versus 2 to 3 months for a typical steel footbridge. And the prototype installation, we actually reduced it from 3 weeks down to 1 week on site. It has 20% lower carbon footprint than other structures, and the overall whole life cost and maintenance is 40% lower. And we have integrated structural health monitoring system in it because, I mean, it's an innovative design, but we're still learning to see how it behaves and see how we could improve on it. So yeah, it's an enjoyable design. Thank you very much.